Okay, so in the last class we discussed about this successive loop closure where we were using our rudder angle delta to make sure that so we are controlling rudder angle to ensure that chi is tracking chi d, and then on top of that there is a second loop which is trying to ensure that the YPE is going to 0, or that is being tracked to 0 by providing the proper heading angle, not the course angle. Proper course angle, not heading angle. By controlling chi. So that's what we were looking at last time. So loop closure is one easy way to go past or to design a successive set of PID controllers in order to ensure that our dynamics of the plant behaves the way that we want it to behave, right? So we've looked at some of these ideas. Let's formalize this concept of pole placement algorithm, and we'll try to relook at it from the point of view of a spring mass damper system, then try to see how that can be applied to a single input, single output system. And then we'll try to also see how we can extend that for multiple input, multiple output system. And we'll try to see how this PID control and pole placement algorithm works for us in this particular case. So we have already seen this before, so I'm going to be a little quick on this part of it. We have seen a spring mass damper system, which can be expressed in a standard form as this, where we are expressing in terms of the natural frequency omega n and the damping ratio zeta. And they can be related back to the mass, damping, and the stiffness of the system. So it is clear that for this sort of a system, the transfer function has two poles which are located in the left half plane, in the complex S plane, at minus zeta omega n real part and j times omega d, the imaginary part. So which is the oscillatory component, and then there is a decaying component which is located at the minus zeta omega n. So I can represent this minus zeta omega n as, zeta omega n as A. So then my poles are actually located at minus A plus or minus j times omega d. Okay, and omega d here represents the damped natural frequency, which is not the same as the actual natural frequency of the undamped system. That is different. That is what we represent by omega n. And we know that the relationship between omega d and omega n is known to us. Omega d is omega n times square root of 1 minus zeta square. Okay, where zeta is the damping ratio of the system. So if I put them on the complex plane, you will see that the two poles are located here and here. They are complex conjugate poles, with the real part being minus zeta omega n and the imaginary part being j times omega d. So it is easy to see that this so-called angle, which the line joining the origin to this pole point, makes an angle phi, and we can see that actually cosine of phi is nothing but zeta itself, because this is a right triangle whose one side is A, the other side is omega d. So let me try to draw this triangle somewhere here. So this side is omega d, this side is minus A. So this side will be square root of A square plus omega d square, which is nothing but omega n square. Actually omega n. Okay, you can see that very easily because A is nothing but zeta omega n, and omega d is nothing but omega n times square root of 1 minus zeta square. So when I take A square plus omega d square, I'll get zeta square omega n square plus omega n square 1 minus zeta square, which will be left with omega n square. So therefore this triangle has its hypotenuse as omega n, and the other two sides are known to us. So we can actually find out what is the value of this angle phi. So that angle phi is nothing but cosine of that angle phi is equal to the damping ratio. Is everybody following me? Okay, so basically if I wanted to figure out what is the damping ratio, all I need to calculate is what is the angle this line joining the origin point to the pole makes with the x-axis. If I know that angle, I can precisely figure out what is the value of the damping ratio in my system. These are stuff which we have seen before. We are just trying to summarize it here at one location, that's all. So we're not adding any new information per se here. The undamped oscillator is obtained by setting A equal to 0. So since A is equal to zeta omega n, we are essentially setting zeta equal to 0. And in that case, we can kind of see that the poles will translate onto the imaginary axis. So the poles will now come by and be located on the imaginary axis. And omega d will also become equal to omega n in this particular case. Is everybody following me so far? These are spring mass damper system which we have already discussed maybe a couple of times before. So this is just a summary of what is going on, that's all. Okay, in a typical case where we do have damping in the system, it might be convenient to express the so-called damped natural frequency as some reduction factor R times the natural frequency of the system omega n. Okay, the idea being that this R is the value which I might be using as a design parameter later on. So we'll see how that gets used. So if this R is taken as the so-called reduction factor, we'll see that for most typical marine crafts, this reduction factor is about kind of close to 0.5%. Okay, and therefore we will see that this R value which corresponds to it will be actually equal to 0.995. Okay, that reduction factor is 0.5%, so the R value is 1 minus the 0.5 by 100, which is coming out to be 0.995. If we put it into our expression, we can find that the value of A is square root of 1 minus R squared times omega n, and for R equal to 0.995, this corresponds to a zeta value, where this thing is zeta, to be equal to about 0.1, which is quite typical for ships. So this is an alternative way of looking at it. So rather than specifying what is the damping ratio of the system, I might specify things sometimes in terms of R and then relate R to the damping ratio of the system. So you'll see that commonly many times in the marine practical side of the things, they will not be pretty sure as to know what is the damping ratio, or they may not have an understanding of what is a damping ratio, but they'll have an understanding of what is this reduction factor. So that reduction factor can be related back to the damping ratio, as we are seeing here. So it's only a practical terms, a different methodology to discuss the same concepts. So there is no difference in the concept, but we are expressing it in terms of R as the design parameter instead of zeta as the design parameter. Okay. So sometimes you'll see that from a practical standpoint of view being used in many places. Okay, what you want to probably take away from this is typically for the seakeeping modes, a damping ratio of 0.1 is more or less reasonable enough, especially in the roll mode of motion. And for typical ships with a bilge keel, zeta equal to 0.1 is a rule of thumb approximation which you can make in order to determine what is the damping ratio for roll motion. Pitch and heave generally have a little bit more damping than the roll, and therefore you will expect to see a little higher damping ratios corresponding to zeta equal to 0.2. So the idea here then becomes that if I know this value of R, which is my design parameter, that will help me fix zeta, and once I know zeta, I can figure out what is the actual damping present in the system. I can get approximate expressions. Please understand that these are rule of thumb. I'm kind of saying that back of the envelope calculation, if we wanted to do, how would I go about finding out what is the damping in ships? Typically, we know that the damping will not be constant. We know that it is actually frequency varying because the radiation damping will depend on the frequency of the wave that we are trying to excite it with. So all that being kept aside, I'm just giving you a rule of thumb methodology to figure out what the damping is in a vessel. So if I know what is the mass and the added mass, and if I know what is the stiffness, I can predict what the damping is as long as I figure out what my damping ratio is, which I can grossly approximate as 0.2 and get away with it. Okay, but this is only for a purpose of gross approximation. Please do realize that whatever we discussed in terms of modeling sense, that when we are actually looking at your seakeeping motions, the damping will be frequency dependent. So it's not going to be looking exactly like a constant here. This is a practical sense. If I want to get an estimate for what are the damping values, I can get them in this manner. Okay, so this is quite useful to have this linear damping in heave, roll, and pitch being predicted. So as long as I know the mass and the added mass and the stiffness, and we know the different methodologies to obtain this, once the geometry is known. So if we know the vessel's displacement, and we know the added mass of the vessel, and we know the stiffness of the vessel, we can preferably be able to compute the damping in the system as a gross approximation. And that can be used for our control system purposes, because we don't need a very high fidelity model when we are looking at the control system. We can get away with a reasonably moderate plant. Now this method works very well, where I specify a value of R, which gives me a damping ratio, which will give me what is the damping in heave, roll, and pitch. Works very well for the seakeeping modes, but the same thing does not work for the maneuvering modes for obvious reasons, because there is no stiffness in the maneuvering modes, right? So there is no stiffness in the maneuvering mode, so therefore I can't use this approach. In fact, if I attempt to use it, I'll find my damping actually comes out to be 0, right? So therefore I have to evolve a slightly different methodology in order to figure out my damping for a rule of thumb calculation of damping in maneuvering modes. That we do by specifying a time constant. So here we are looking at systems which do not have any stiffness in them, and we try to express this system as in terms of something which looks like our Nomoto's equation. Okay. So where we are specifying things in terms of time constant. So as long as we specify a time constant, I can say that the damping can be evaluated as we are seeing here. Where basically I'm making a comparison between the spring mass damper system and the time constant based system, and deriving the relationship that basically this value of T is nothing but m by d, and therefore d will be given by m by d. So as long as I know the mass of the system and I specify some time constant. So let us say I took our KCS model. I don't know what is the damping in it. I just take it and apply a steady rudder angle and see how long does it take to asymptotically reach a steady heading angle. From that, I'll be able to predict what will be the value of T, and from that, I'll be able to predict what should be the damping that I need in my yaw. Okay, so that's more of from a practical point of view. Let's say that our KCS model, we wanted to estimate what is the damping in the yaw mode. Then we can use such methodologies there more fruitfully in order to determine. But again, please do understand that these are approximate methods to determine the damping, because damping is a quantity which is not very easily determinable. You require really a lot of experiments, and many a times even your experiments will not give you what will happen in the prototype scale because of the scale effects coming into the picture. So therefore, it becomes important to figure out what is the damping in my system. So I'm giving you approximate methods to determine the damping in seakeeping and maneuvering modes. Is everybody with me so far? Yes? All right. Okay, so suppose that I wanted to look at the single degree of freedom yaw mode of motion. Okay, where I'm assuming that I'm going through a pure yaw motion where there is no sway motion. So in that case, my equation of motion can be written as Iz minus nr dot. So this is the mass moment of inertia and this is the added mass. And then this is the damping term, and then I have the external force which is coming from the rudder. It's a very simplistic representation, but just say that I know what is Iz minus nr dot, and I want to figure out what is this value of nr. I can specify a time constant in yaw, and then based on that I can specify what will be my value of nr. And this time constant you may get either from experiments, or you may get them from some other methodology, or it may be a design parameter which you are choosing. You are saying that my yaw should try to stabilize to a particular heading angle within so much so time. Then you can figure out what is the value of this time constant. And therefore, in essence, you can predict what is the damping which you require in your system. Okay, so that was just a way to predict the damping terms in all the different modes of motion when we don't have much information about the plant. If you have more information about the plant, obviously you want to use the high fidelity information for designing your control system. But if you don't have it, this is a methodology which you can use to get some approximate numbers to get your control system process started. Okay, now let's try to look back at our linear PID control, which we did take a look, but we'll kind of look at it in a formal sense and define a few new terms in terms of what is called as the bandwidth, what are the mathematical expressions for bandwidth, how does that affect our control system. We'll try to discuss that. We have seen this before, that in this case of a linear PID control, the control input is going to be some proportional part times the error, some derivative times the derivative, and integral times the integral of the error. So that is the PID controller part. But you'll also typically see that there is an added component k times xd, which is added to your control law, which is called as your reference feed forward. So what your PID law will do is it will try to ensure that x tilde is going to 0, but you want to also make sure that if you want to track a specific reference value rather than the xd being 0, then that reference value also has to be given into your control signal. It's more like a constant term that I'm asking my system to now track, right? So if we provide this control input to our system, we should ensure that the control input will now ensure that x is now tracking xd, or x tilde, which is given by x minus xd, is tracking 0. Where kp, kd, and ki are greater than 0 and are called the controller gains, and then x tilde is x minus xd. Here we are assuming that xd is constant. If xd was not constant, you would see that instead of x dot here, it would have been x tilde dot. And that would have been the difference in your PID controller. Okay, for simplicity, let us assume that for now ki is equal to 0, so which means the integral component is 0. Then the closed loop system basically becomes mx double dot plus d plus kd times x dot plus k times kp times x tilde is equal to 0. And you will now see that the reason why I wanted to put that k times xd in here, this term in here, so that I can actually get this k plus kp times x tilde. Otherwise, it would have been k times x plus kp times x tilde. Right? Everybody with me so far? I'm looking at a few blank faces. Why? Yes, Anand?
Try to understand this.
Anand, I can't hear you.
Sir, I didn't understand that last part.
Okay. So let us say that this part is not there. Okay. Tau is simply given by let us say tau is simply given by minus kp times x tilde minus kd times x dot. Okay, now we have our system mx double dot plus dx dot plus kx is equal to tau, correct? So by putting the expression for tau into here, what do I get? Mx double dot plus d plus kd times x dot plus k times x plus kp times x tilde equal to 0. Okay. The point is, if I had added the term k times xd here, if I had added that term, then this would have become x times k times x tilde. Yeah, that's what I was saying. Basically, algebra that I was talking about. Yeah. Okay. So from here, you can see that basically, if we want our pole placement method to be figuring it out, we want to figure out KD and KP in such a manner that the system exhibits some damping ratio and some natural frequency, which means in the S plane, I'm basically specifying how far these poles should be from the origin. This distance being omega d and this distance being a, which is zeta times omega n. So if I know what is zeta and omega n, I'm basically specifying where are the poles located in my complex S plane, and I'm trying to make sure that I choose Kp and Kd values such that this zeta and omega n are satisfied. So I can rearrange these terms which you see here in order to get my expressions for Kp and Kd, and it is easy to see that you can figure out Kp is m omega n square minus k, and Kd is 2 times zeta times omega n times m minus d. So as long as I know the parameters of the system, the mass, damping, and stiffness, and I know where I want to place my poles, I can choose my controller gains, okay, such that the desired behavior can be found out. And this is where it becomes important. I may know the mass and the stiffness very easily. Many times I may not know the damping precisely. So that's why the damping can be approximated using the methods we just discussed. And then you are choosing your poles to be at a certain location and then applying these methodologies to determine your controller gains. Okay, it's a rule of thumb to get your controller gains, but please make sure to understand that once you determine your controller gains, you have to actually do the simulation with a high fidelity model to verify that actually your control system is working fine, right? Preferably, actually, if you have a model where you can actually test it in experiments, one would want to do that rather than do simulations to verify that those gains are actually leading to some good results or not. All right. Okay, so in this case, we can see that the transfer function between the x and xd simply is given by omega n square by s square plus 2 zeta omega n s plus omega n square. And this is where we are looking at the so-called PD control law. So notice that we had started off with our idea that Ki is equal to 0. Now suppose if I wanted to bring back Ki greater than 0, because I wanted to compensate for constant and slowly varying disturbances, then in the Laplace sense, my control law can be written again as this, where you are now seeing that the integral term has made its way back into our system. But you'll notice that when I wrote this control law here, I'm not expressing it in terms of Kd and Ki, but I'm expressing it in terms of some parameters Td and Ti, where Td and Ti are actually relating to Kd and Ki using the expressions which you are seeing here. The idea here then becomes that rather than choosing a value of Kd and Ki, which are gains which don't have a physical significance, I may rather want to specify them in terms of some time constants which may have more practical application or practical relevance, and then try to determine what should be KD and KI depending on these time constants. So rather than choosing these values independently, I would choose the values for Ti and Td, which will in turn control what should be the value of Kd and Kb. Everybody with me so far? I'm just trying to give you these methodologies as an understanding that sometimes some of these quantities may not have a physical meaning, and we want to convert them into quantities which may have some practical meaning and use them to tune our gains rather than tuning some arbitrary numbers. Everybody with me? Krishna Velu with me? Okay. All right. Now, when you typically look at a rule of thumb, as I said, this integral gain, you want to keep it to be pretty slow. You don't want that integral gain to be very big, because what will happen if the integral gain is very big, it is basically integrating the error over the time, right? As time increases, that integral terms, integral over 0 to t of the error will also keep increasing. And therefore, it can start having a very wonky behavior. It can lead to very large overshoots in your system, which means that if I ask it to track 10 degrees heading angle, it may go all the way up to 30 degrees before it comes back down and starts to stabilize at 10 degrees. So this integral term, we want to make sure that it's not varying very quickly. So this coefficient Ki, we want to keep it as low as possible typically. And the rule of thumb which we choose here is that rather than choosing Ki, I'll choose it or express this in terms of 1 by Ti is approximately omega n by 10. So which means that the integrator's time constant at least is 10 times lower than the natural frequency of the system or the natural period of the system. Okay. In some sense, I'm missing a pi there somewhere. Yes, you're not. It's not a precise expression. It's more of an intuition that I'm trying to make sure that you understand. Okay. So I want that integral time constant to be representatively close to about omega n by 10. So that the integral gain will vary much more slower compared to the proportional term, so that these overshoots can be avoided, but at the same time, steady state error can be made to 0. Okay, the idea here is that the integrator is at least 10 times lower than the natural frequency of the system. So then I can get my Ki value as omega n by 10 times Kp value, which was omega n square times m minus k. So given a mass, stiffness, and damping values and where I want to place the pole locations, I can figure out what should be my proportional derivative gains first, and then once I have those gains, I can figure out what should be my integral gain. So I'm basically giving you some methodology to tune your PID controller. What should be the steps to go about it? And you'll see that I'll formalize it even more as we go around. Okay, now is a good time to discuss about what is this so-called bandwidth. The control bandwidth omega b, which we define as how much is the range of frequencies at which, or nominally it is the range of frequencies at which our control functions were, is taking the input signal and transferring it back to the output, is what we define as the control signal's bandwidth. Anything beyond that bandwidth, we are rejecting those frequencies. We are not trying to track those frequencies. So let's try to come up with a more precise definition for this control bandwidth and see how it can actually be related mathematically to our expression for natural frequency. So far we have only talked about this in a physical sense. I only qualitatively discussed about bandwidth. I've never mathematically put down the expressions for what is the expression for a bandwidth. So let's try to see what is those expressions for a bandwidth. So if we look at the system which you see here, so h of s being the plant, whose output is y, and it takes as an input u, which is taking actually some reference value r and a feedback from the output. Okay, this is the simplest of the feedback systems which we can construct, where the feedback is simply unity. I'm taking the output and directly feeding it back in, right? The idea here is I want to look at the so-called loop transfer function, which means if I start at any point in the loop, if I break the loop at some point, let's say that I make a break here. So I want to see from here to here, what is the input to the output ratio? That is what is representing my loop transfer function. In this case, you can see that that loop transfer function is nothing but h of s times unity. The unity is coming because of the feeding of my output directly to my input. On the other hand, suppose my system was something like this, h, and then I have some n. And if I wanted to find the loop transfer function, in this case, it would be h times n. Correct? So basically, n is the transfer function. So that it's basically saying that suppose I feed something here, and I want to look back what comes out if there is a break in the system. And this loop transfer function has a lot of importance. It tells you when my system can become unstable. Okay, if I feed some signal amplitude of unit amplitude and I'm getting back the output as something greater than input, then it means it's starting to amplify my signal. That's what it means, right? If instead the amplitude is lesser than my original amplitude, it means that it's trying to damp out the system. So over time, everything will damp out. Okay, so when I tune my feedback gains, I want to make sure that the system remains stable, that this loop transfer function is not doing some crazy things. You remember, if you have ever observed in our online meetings, if I ever join by, sometimes we get a feedback in our system, right? So I speak something, but then it gets amplified and keeps getting amplified and over and over and over again. So what is happening there? My speaker is giving out the output, which is being picked up by my microphone, and then it's getting amplified again and again and again. Okay, so this same exact process is happening there. So when your loop is not stable enough, if the loop's transfer function is more than 1, it's trying to now say that I will now amplify your signals in a certain range of frequencies. So it might so happen in such cases that if I am speaking, the feedback may be there, but if somebody else is speaking whose frequency of voice is slightly different, the feedback may be different in their case. Right? So I'm just trying to give you a practical example of this loop. Okay? It has nothing to do with our system for now, just an example. So the idea here is that we want to figure out this loop transfer function, which we will represent as L, okay, which in this system's case is h times 1, otherwise it would have been h times n, as you saw here. Where is that frequency when this loop transfer function's value becomes 1 by square root 2? That value of omega b is what I want to specify as the bandwidth of the system. Okay, so it's basically telling me if I make a plot of that versus frequency mod of L, up till what point it remains flat and then what point it dies down. So this is saying that where does this value become 1 over square root 2. Okay, that is the range of frequencies for which this loop transfer function is operating. Anything beyond that, it is damping out things. Okay, so that represents my so-called bandwidth of the system. That is the mathematical definition. Sometimes you'll also see that control engineers might specify this in terms of decibels. So what they are saying is 20 times the log of this transfer function should be equal to -3. And you'll see that these are not exactly equivalent. So this corresponds to 1 by square root 2 corresponds to about 0.707. This will correspond to some approximately 0.86. Okay, but it is very common to see both of these come up when people are trying to figure out what is the bandwidth. Okay. So they may either express it in terms of 1 by square root 2, or they may express it in terms of decibels. The second one being more popular with the control engineers in the electrical engineering department. For our purposes, we will mostly stick to this definition of 1 by square root 2. That makes much more sense for us. Okay, which means that the power is actually becoming half. That's what it means. An input signal's power becomes 1/2 by the time it passes through. Okay, now if we want to look at a second order system, which is given by our regular spring mass damper system as the H of S, which means that is what is this fellow, the plant, and we are looking at a unity feedback loop for that system, it can be shown that with a negative unity feedback, this system's bandwidth can be expressed in terms of the natural frequency and the damping ratio. And you see that big expression come up. And I'm not now going to derive that expression. You're going to have to take my word for it that omega v will be coming out to be that. If you're really curious about finding that out, be my guest, substitute h is equal to 1 by square root 2 and try to solve for what should be the value of s. And then you should basically come up with this expression which you see here. Okay, that is the idea. So you can see that if I know for a second order system, if I know the natural frequency and the damping ratio, I can specify the bandwidth. Okay, or in the other way around, suppose in a control systems engineer perspective, they would not want to specify where omega n would be, but they want to probably specify what the bandwidth would be. Remember that when we were doing successive loop closure, we wanted to ensure that the inside loop has a bigger bandwidth than the outside loop. Right? So sometimes we may not want to specify in terms of omega n. Rather, we want to specify, I want so much bandwidth on this system. Okay, and from that bandwidth and a damping ratio, I need to be able to compute what my omega n looks like. So a typical control process, if I want to summarize everything that we have talked about today, like PID pole placement algorithm, especially for a single input, single output system, is that we typically want to specify some bandwidth greater than 0, specify some damping ratio greater than 0. That will give me what my natural frequency of the system is, assuming that it's a second order system. Then I can compute my P gain, D gain, and I gain, which is 10 times lower than the P gain. Okay, and that is how I will tune my system in order to follow the dynamics that I intended to follow. So notice here, what are the design parameters here? The two design parameters are the bandwidth and the damping ratio. So if I specify how much is the bandwidth and how much is the damping ratio, we should be able to tune our gains of the controller. It gives you a methodology to tune the gains of the controller so that it follows the dynamics which you are intending it to follow. So let's try to see if we can apply this to a simple ship autopilot design and see what happens. So we have our regular Nomothos model, which can be expressed in terms of psi as this. And for this second order system, it is easy to see that the damping is, the stiffness is 0, the value of D is 1 by K, and value of M is T by K. Please note a distinction here that this is capital K here, which is representing Nomothos gain. That is what is used here and here. This here represents the small k, which is the stiffness in the system, which is 0 in this particular case. Okay, so once I know what is the bandwidth and the damping ratio, I can compute omega n, and since I know m, d, and k values, I can figure out what my controller gains will look like, and in this case they can be expressed in terms of the Nomothos constant and the bandwidth and the damping ratio. So once I can specify, once I know what is the value of the bandwidth and the damping ratio that I want to take, I can tune my Nomoto gains heading controller with these gains in order to make sure that this works out fine. An interesting experiment which one can conduct, given that I'm looking at this and I'm thinking off the top of my head, that we have an IMU on board our ASV, correct? Now the idea is that if you can provide a control, if you can tune the controller gains in such a manner that it follows the heading precisely, then you can tune your gains using these methodologies. What you require here then will be what is the Nomotos time constant and what is the Nomotos gain. And how can you get that? I can run a turning circle maneuver and I can see what is the turn rate that I'm getting, and the turn rate will directly relate back to my Nomotos gain. Right? Similarly, after I apply the rudder, how long does it take for my R value to stabilize? Will give me what is the value of the Nomotos time constant. Using those two values, I can figure out if I want to specify a bandwidth and a damping ratio, I can tune the gains of my controller. Is everybody following me? So please understand, I don't know much information about my vehicle. I don't know its hydrodynamic coefficients and derivatives to formulate a high fidelity model. I can still get a few estimates by performing some few tests. I can apply a rudder angle and see how long does it take for the rudder angle to stabilize, the yaw rate to stabilize. That will give me a value of the Nomotos time constant T, and what value of the heading angle does it, the turn rate does it asymptote to, will give me the value of the Nomotos gain K. Once I know those two values, I can predict a good amount of, I can predict the tune, I can tune the gains of my controller in order to do the matching. Okay, so technically if I took it to the field without knowing anything about the vehicle, I still should be able to get a decent heading controller in place by doing these exercises. Okay. Now you're starting to see the power of these methodologies, that we don't need to know a precise modeling of the vehicle, but still be able to give a good reasonable controller in place. Okay, so I'm going to stop right here for today because I don't want to start the next topic and leave it in between. So the next topic we will look at, so this one we have looked at single input, single output. So which means a scalar input and a scalar output. In this case, let's say the ship autopilot design, rudder angle is the input, the scalar input, and the output is the heading angle. We want to look at what happens when we have multi-input, multi-output systems. So if we want to control position and orientation at once, then that becomes a problem of multiple input, multiple output systems, where you may want to control the propeller and the rudder together, and you want to see the control being affected in the 3 degrees of freedom model, X, Y, and psi. Okay, we'll try to take a look at how to deal with MIMO-based systems, and we'll actually look at a nonlinear PID control law for this purpose. You'll actually see that that so-called modeling which we spent a lot of effort on to figure out our Coriolis matrix and all those different matrices, it comes in very handy. In fact, we'll show that that matrix being skew symmetric, the Coriolis matrix being skew symmetric, will help us take certain advantage in designing this nonlinear control law. And we'll be using Lyapunov methods to demonstrate that this control law, PID control law that we'll come up with, will be globally asymptotically stable. Okay, so brace yourself. Coming lecture, we're going to start discussing about that. I still have some time, so maybe it's not a bad idea to look at it. Maybe let's take a look at it. Let's go. So in a MIMO-based nonlinear PID control, we are going back to our original equations of motion, which we formulated in the vector sense, right? We had eta dot, which is our position vector, which could be a 6 × 1 vector if we were looking at a 6 degree of freedom system, right? where eta would be having x, y, and z, and the 3 Euler angles, right? Or it would be having x, y, and z and 4 quaternions, if we really wanted to go that way, right? And then we are looking at the velocities. This is looking at the body fixed frames velocities, which are looking at the translational modes and the angular velocities. And we have seen this before. There's no need for me to spend any more time on this. Am I right? We've seen this before. Now, the idea here is that we will assume that eta and v are known to us. Okay? This control methodology will only work as long as I have complete knowledge of where my position is and what my velocities of the vehicle are. And I'm here assuming that either I'm directly measuring those quantities or I'm actually estimating them using a state estimation method. We have not talked about state estimation so far, but just imagine that we know those quantities is what we are presuming. So if I know all of these quantities, then I can devise a control law which looks like this, okay, where I am saying that there will be compensation for the gravity terms. So tau will be g of eta. So basically I'm substituting tau is equal to g of eta. So therefore this term will basically cancel out on both sides. Okay, so compensation for any gravity terms, and that's more relevant actually for underwater vehicles, where I want to make sure that buoyancy is matching the weight or things like that. Okay, if I want to control how much the submarine is going down, that is where this thing will come into picture. For most of our surface craft application, this vector will not be there, because if you are looking at 3 degrees of freedom search, sway, and yaw, you will not actually see anything come up in this g of eta. This vector itself will not be there. Okay, and then in addition to that, I'm adding this component j of theta transpose times tau PID. So you will see that this tau PID has the same methodology as you saw before, some proportional part, some derivative part, and then some integral part. But notice that how this tau is actually not just given as equal to tau PID, but there is some j transpose times PID. Okay, and that is what makes this system nonlinear. The control law is not linear because we are now introducing these kinematics which are consisting of trigonometric functions. So therefore the system is no longer linear. Okay, so again as before, for practical purposes, let us choose Ki to be 0 to begin with. We will come back tuning the Ki at the end of the day. So we'll first try to figure out what should be Kp and Kd, and then we'll try to come back and see how the Ki affects the stability. So if we assume Ki is 0, then my control law is simply minus Kp times eta tilde minus Kd times eta dot. Okay, where again I'm following the same convention as before. Eta tilde is eta minus eta desired, and we are assuming that that so-called desired value is fixed. It's not changing with time. Okay, so I'm doing some set point regulation is what I'm presuming. So if it is a surface craft, I might be saying that I want to be in some XY location with a certain orientation of my craft. I want to maintain the orientation of the craft. Okay, so by putting this control law, substituting this control law tau into our equations of motion, you'll see that this thing becomes mv dot plus c, which is the Coriolis matrix, the damping matrix. Now there is an additional term which is coming due to the derivative part of the controller. I'm calling it Kd star to differentiate this from Kd, because Kd will be different from Kd star. And that will stem due to the fact that I'm multiplying by this J transpose somewhere. So we'll see what that expression for Kd star is. And then we'll have plus J transpose Kp times eta tilde is equal to 0. So this is what I get my equation of motion transforms into by substituting tau is equal to this control law which you see here. Notice that as I said, this Kd star is nothing but J transpose Kd times J. That is what will come out from the algebra. Okay. Again, now we'll try to apply Lyapunov stability theory in order to understand why this controller is chosen in this particular way and how does it guarantee us certain stability properties. Okay, so if we assume that we are looking at a set point regulation, which means we are trying to track eta d equal to some constant value, I can specify my Lyapunov function as 1/2 times V transpose M times V plus 1/2 eta tilde times, sorry, there should be a transpose here, Kp times eta tilde, where I'm assuming that this Kp matrix, which is the proportional gain term, is a fixed matrix, which means that its gains are not time varying, at least. Its gains are fixed, and I'm assuming that it's a symmetric matrix. Okay, it is symmetric and positive, definite. So then you can see that this part somewhat represents the kinetic energy of the system. Okay, and the second part represents the so-called potential energy due to that artificial spring I'm putting in place due to the controller. There is no specific spring in place here because I don't have any stiffness in surge, sway and yaw, but it's an artificial spring which I'm putting in place due to the proportional part of my controller. So the addition of this potential energy and kinetic energy becomes my new Lyapunov function candidate, whose dynamics I'm going to start looking at. So if I take a derivative of that, it is easy to show that since mass matrix and this Kp matrix are both symmetric matrices, I can express this as V transpose times M times V dot and eta dot transpose times Kp times eta tilde. So I'm basically taking a chain rule of derivative. So when I take a chain rule of derivative, actually I should get two terms. I'll get something V dot transpose M times V plus V transpose M times V dot. But as long as M is symmetric matrix, these both terms are the same terms. So I can write one in terms of the other. Okay, that is why you're seeing that I can express that in terms of only one times, the derivative being only on one side. Is everybody following me?
Yes, sir.
Yes, okay. Similarly, since I'm assuming Kp is also a symmetric matrix, I can do the same for the eta case as well. Okay, only case here, the derivative when I take eta d dot will be 0. So that is why I'm being left with only eta dot, because eta tilde is eta minus eta d, but eta d dot is presumed to be 0 because I'm trying to look at a set point regulation for now. Okay, putting both of these together, now I can express this eta dot transpose as J dot transpose times V dot, right? So I already know that eta is J of theta times V. So if I want to write down eta dot transpose, that will be V transpose J theta transpose. Okay, so that I'm substituting in respect to this fellow. All right. Once I do that substitution, I am taking this V transpose as common between both these terms. So I am left with M times V dot from the first term. And in this case, I am left with J transpose times Kp times eta tilde. Everybody following me? Krishna Velu following me?
Yes, sir.
All right. Now, I can express now I can see that m v dot plus j transpose times kp times eta tilde. If I look back at my closed loop system, I'm basically having this term plus this term. That is what I'm seeing there, right? That is nothing but equal to negative of this term from my closed loop dynamics. So I'm going to replace it with that, and eventually I'll get, instead of this mv dot plus this thing, I'll get c times d times kd star times v. This is the expression I'll get. Everybody with me so far? Now, as long as I can ensure that these matrices are positive semi-definite, then this product will be less than or equal to 0. I can show that because it's a quadratic form, right? Everybody with me? So this product will always be less than or equal to 0, and it is equal to 0 when v is equal to 0. Notice that I removed c of v in this expression when I went down, because we already know that the skew symmetric matrix C will definitely satisfy V transpose a skew symmetric matrix times V will be equal to 0. Okay? Because we know that this Coriolis matrix is skew symmetric, this term will be 0. So what I'll be left with is this, and I know that the damping cannot be a positive negative definite, because damping has to be positive in any system. So it will always be a positive definite matrix, and kd star can be chosen by me, so I can always ensure that it will be positive definite, so that this v dot will always be less than or equal to 0. Okay. Notice that it is equal to 0. Okay, that inequality is not less than 0, which means I have not proved global asymptotic stability yet. Okay, now I will look at all the set of possible values of eta, tilde and v such that this v dot is actually equal to 0. What is that set of values which will cause this fellow to be equal to 0? When is this equality satisfied? And you can see that that is equal to 0 as long as v is equal to 0. Okay. So all the points, wherever my location of eta may be, doesn't matter. As long as v is equal to 0, this v dot will be equal to 0. But then we will try to find out that when v is equal to 0, our equation of motion gives me that mv dot is equal to this. Right? Because if we go back on our closed loop systems dynamics, when v is 0, this term will be 0. So mv dot will be negative of this. When mv dot is negative of that, and let us say that eta tilde is not equal to 0, then v dot will not be 0. So this means that v equal to 0 state cannot be maintained. It will move away from v equal to 0 because v dot is not equal to 0. Because the velocity's derivative is going to next time step, it will now be at some non-zero value of u. So it is not a invariant step. It's not an invariant point in the set. The only invariant point in the set, which means where I start and I continue to be there, is when eta tilde is 0 and v is 0. If I start from that point, I'll definitely continue to be there. But any other point I start, it's not a state that I can maintain. So the highest invariant point in this entire set is only the equilibrium point corresponding to eta tilde equal to 0 and v equal to 0. So the system will be globally asymptotically stable, with that being the equilibrium point. Okay, where we are using our Krasowski's-Lascelles theorem, which we discussed in our nonlinear stability theory. Okay, so the system cannot get stuck at any other equilibrium point other than eta tilde is equal to 0. So therefore, the eta tilde and v equal to 0, 0 is the largest invariant set in the set of points where v dot goes to 0. So therefore, we have that this fellow is now globally asymptotically stable. Everybody with me so far? Anand?
What are the components of theta tilde?
Theta tilde will be a 6x1 vector if it is a full-blown thing, or if we are only looking at surge, sway, and yaw, it will be 3x1. It's basically looking in the difference between the positions, difference between x and y, and then the orientation. Remember that this eta, nothing but the XY position in the NED frame and the heading angle when we are looking at a surface craft. If we are looking at a full-blown thing, then this will be a 6x1 vector where we are looking at X, Y, Z and 3 Euler angles.
So this is NED frame or body fixed?
This is an NED frame. X and Y and are in an NED frame. Okay, so I want to track the position of my vehicle in the NED frame. I want to ensure that it follows a path which I specify in the NED frame.
Sir, so there will be only one stable equilibrium point at the origin, nowhere else.
No. This is eta, but what I'm saying here is eta tilde. Eta tilde is eta minus eta desired. That is the desired point that I want to track. So when eta tilde goes to 0, eta will go to eta d. Okay, so it's not saying that I'll always come back to the origin of my point. No, wherever I chose my desired point, the error between the exact position to that chosen point will be driven to 0. That's what it means.
So there are multiple points like that.
Yeah, depending on where I want to choose it. I have the freedom to choose where the desired point should be, right?
Yes.
And as I choose the desired point at different locations, as my waypoints are changing, it should now start tracking that new point, basically. Okay, it only goes to show that as long as the control law is chosen in this manner, the equilibrium point is stable enough. And it is globally asymptotically stable, so that if it starts at some other point, the craft will approach this point and orient itself into its correct orientation and stay there.
Sir?
Yes.
What if it is between two such points, like two desired points?
I'll only be specifying one desired point at a time, right? At a time, I'm tracking only one desired point. After I have reached that waypoint, I'll track the next one. But at a time, I'm only giving it one input. In fact, you will see that in our line of sight, we may not actually give the waypoint as the input. We may give some look ahead distance and some point on the path as the point which I want to track instantaneously. Doesn't matter. So, but there is a caveat here, okay? We did assume here that eta d is constant. But now we are trying to apply it to things where eta d need not be constant. And yes, it will work there as well, but there may be some stability degradation which may happen. So that's why we have to be a little careful about it. That part definitely does exist. And in fact, you'll see, forget about all that. The moment I add integral action itself, this stability cannot be guaranteed. This global asymptotic stability which we looked at is only for the case where Ki was equal to 0. When Ki is greater than 0, when the integral action is present, I can't demonstrate again global asymptotic stability in that case. Okay, where the maximum I can do at that point is that it is locally asymptotically stable, which means I can't show global asymptotic stability in that case. Okay, there are some studies which have shown that it is possible to prove this. Now we are not going to undertake those proofs in our class here. Just so understand that the methodology is in this manner. So there we can't prove global asymptotic stability. You can only prove local asymptotic stability. Which means that if this value of Ki is too large, my system may potentially become unstable. Okay, that's what it means. Or for a chosen value of Ki, there is only a range of initial conditions in which I am stable, where I am close enough to the equilibrium point that I want to go to. If I'm too far away, then there's no guarantee that I'll be able to approach there precisely. Okay, so we have to kind of live with that fact, but we want to include the integral gain many a times so that our steady state error goes to 0. So it's kind of a balance. It's like a compromise. Do I want to introduce some integral gain and make sure that my steady state error goes to 0, but lose some amount of stability, or do I want to discard integral gain altogether, make sure that my system is globally asymptotically stable, but it may have some steady state disturbance error? So what do I want to live with? So as a control engineer, you have to make that choice and then accordingly tune your gains. Okay, next class we'll look at what to do if I want to place the poles of my multiple input, multiple output system. This MIMO system's poles, I want to place it at a particular location. Pole placement for multiple input, multiple output systems, how to do that. And what we did as a formal algorithm for single input, single output system, we'll try to derive a similar algorithm for our multiple input, multiple output system. Notice here that this controller is nonlinear. The plant is nonlinear, the controller also is nonlinear. Whereas in the linear, the single input, single output case that we looked at, the plant was linear and the system was also linear. The control system was also linear. Okay, so we'll try to see how to do that in the next lecture. Okay, good that I was able to actually cover this today. We will try to reconvene next time and take a look at it forward. Any other questions before I stop recording? No other questions? Let me stop recording.